Illustration of method of section in plain trusses. The method of section will now be illustrated for the truss in the figure shown here. Which was used in the explanation of the method of join before. The truss is shown for ready reference. The external reaction are first computed as with the method of joint by considering the truss as a whole. Let us determine the force in the member BE. If we want to determine the force in the member BE, for example, an imaginary section indicated by the dashed line here. We made a section here. Before that, we calculate these reactions. In pass-through truss, cutting it into two parts. Figure can be re-sketched as this picture after making a section. Consider this picture. This section has got three members whose forces are initially unknown. These forces which are equals to these forces in the other section. In order to portion of the truss on each side of the section to remain in equilibrium, it is necessary to apply to each cut member the force which was exerted on it by the member cut away. Apply to each cut member the force which was exerted on it by the member cut away. For example, we cut a member BE and we should replace with the two forces in each side. For simple trusses composed of a straight two force member, these forces, either tensible or compressive, will always be in the direction of the respective member. The left side section in this equation is in equilibrium under the action of applied load L. The left side, here we have this is left side on applied load and the reaction load R1, and the three forces exerted on the cut member by the right hand section which has been removed. We can usually drop the force with their proper sense by a visual approximation of equilibrium requirement. Thus, in balancing the moment about point B, for example, this point, if we make a balance, point B, For the left-hand side section, the force EF is clearly to the left, which makes it compressive because it acts towards the cross-section of member EF, this member. The load L is greater than the reaction R1, so that the force BE must be up and to the right to supply the needed upward component for vertical equilibrium. Force BE is therefore tensible since it acts away from the cross section. With the approximate magnitude of R1 and L in the mind, we see that the balance of moment about E here can be directly computed. The force BC or B if we make a BE can be calculated. Require that BC to be right. BC and we can be calculated. A casual glance at the truss should lead to the same conclusion when it is realized that the lower horizontal member will stretch under the tension caused by bending. The equation of moments about joints B eliminates three forces from the relation, and EF can be determined directly. The force BE calculated from the equilibrium equation for the y direction. Finally, we determine BC by balancing moment about point E as written here. In this way, each of three unknowns has been determined independently of the other two. The right-hand section of the truss is in equilibrium under the section R2 as shown here, and the same three forces in the cut member applied in the direction opposite here to those for the left section. The proper sense for the horizontal force can easily be seen from the balance of moments about point B and E. Additional consideration in the next section.